didn't really pick that operator at random. I'm sure you realize that I didn't pick it at random. So what principle did I use in picking that operator? Notice that the suppression of A over lambda comes about associated with the dimension of the operator that we're including for the interaction. The lower the dimension of the operator, the fewer powers of A over lambda. And so it's very simple. I looked at this and I said, the scattering will be dominated by the operator of the lowest dimension. And then I knew that I needed at least 2 powers of the electric field in order to have an interaction which modifies the incoming photon to the outgoing photon. I needed a phi dagger, to modify the incoming molecule to become the final molecule. But anything else was going to increase the dimension of the operator, and therefore I knew that all those other choices with more derivatives, more fields, would make negligible contributions to the scattering process. So what's the logic I followed? I found the lowest dimension operator that can contribute to the scattering process. It's that simple. And once I did that, I got the answer that Raleigh got. Okay, so this is the crux of the matter, that it's not that I knew in detail what the interaction should be. In fact, what I think the real Lagrangian is, characterizing the interaction between that nitrogen molecule and incoming light, is not the operator I wrote down. It's all the operators, including arbitrary derivatives, including arbitrary fields, extra phi's, extra e's, the b's that we ignored, all of that. And they're all present with coefficients that I know nothing about. It's not that I think that I hit naturally upon the right interaction. All of them are present. But the one I wrote down is the only one that makes a significant contribution in the limit where the wavelength of light is long compared to the Bohr radius. Okay. This, what might seem like a really simple, naive observation, is the heart of our modern understanding of field theory. It sometimes goes by the name of effective field theory. Why the name effective? Because if I know that I'm working in a certain momentum regime, in this case the wavelength of light being long compared to the characteristic size of the nitrogen molecule, then the Lagrangian, which in principle contains every possible operator, that is to say, every possible interaction, I can ignore almost all of them. I only need to keep the most relevant interaction. And most relevant means the one that makes the largest contribution, that is to say, the one of the lowest dimension. And that's the name of the game. Once I know what the particles involved are, I can identify the associated fields. In this case, it was photon-nitrogen scattering, so I needed a photon field, I needed a nitrogen field, and I just have to construct the interaction of the lowest dimension I can find, and I'm done. Now, what, yes, Jordan.
Yeah, yes. I was just wondering, how do you quantify which, how do I formulate this? How do you define, why does it always have to be the contribution which gives the most contribution to the scattering? What if, for example, it turns out that the scattering is extremely weak with a very small cross section, and that actually the more suppressed solution is the correct one? Could that be a possibility?
Right. Yes, absolutely. So let's be clear about this. Let me just restate what you said, is that, of course, by writing down the interaction that I have here, okay, I wrote down the one that will make the largest contribution. But of course, it involves this unknown coefficient C. Maybe, for some very strange peculiar coincidence, the constant c turns out to be really, really, really tiny. Well, then, even though any other operator I could have written down for the interaction will make a contribution that is suppressed by powers of a over lambda, maybe that would dominate just because the coefficient c turns out to be extremely small. That is a perfectly logical possibility. But let me point out that in this particular case, for example, the next most relevant operator is the one with the 2 extra derivatives, which we said was smaller than the one that I wrote down by 12 orders of magnitude. That is, say it made a contribution to this scattering that was smaller by 12 orders of magnitude. The only way this one could be important is if somehow the coefficient c turned out to be small as 10 to the minus 12. Okay, did you get that?
Yeah.
So, can that happen logically? Yes. Does it ever happen? No.
Okay. Is this verified? Is this somehow observed experimentally, or?
Absolutely. So the technique that I'm describing here, which I will say a bit more about in a second, more formally, is well understood and applies in pretty much every experiment we ever do. Okay, and there are no known cases. Now, I will tell you that there are some cases where the suppression, so why did we get such a small suppression of this additional operator, the 12 orders of magnitude? It's because there was a very large hierarchy between the Bohr radius, 10 to the minus 10 meters, and the wavelength lambda, 10 to the minus 7 meters. So for every factor of a over lambda, we got a suppression of 0.1%. Right? That's where the 10 to the minus 12 came from. There are plenty of examples where that hierarchy of scales is a lot narrower. Maybe it's only 1 order of magnitude. So then, and then there are situations where the new operator is suppressed only by an extra a over lambda squared instead of a over lambda to the 4th. So then it would have been a 1% thing, and if you have a coincidence where the coefficient is as small as 1%, there might be competition. Now, I can tell you that I actually, off the top of my head, I know of only one case out of the literally tens of thousands of times people have applied this. I know of a single case where arguably a higher dimension operator actually makes a contribution which is competitive with a lower dimension operator. Okay. But let me point out that that's not a tragedy. It doesn't mean there's anything wrong with this. So notice, if we had computed this and then gone out and measured the scattering and discovered, hey, it's not going like 1 over lambda to the 4th, it's going like 1 over lambda to the 8th, we would have known that this operator has a very small coefficient. In particular, it's actually a measurement of the small coefficient. Does that make sense?
Yes, I think that makes sense. Thank you so much.
Okay. So, I'm emphasizing this for a couple of reasons. So first of all, it's obviously extremely useful. Just understanding this simple principle means you can do all sorts of calculations that you previously probably have done and have struggled with. So let me give you a little homework assignment just to see how all this works. So you all spent a lot of time as undergraduates doing quantum mechanics, and you learned about the hydrogen atom, and you know there's the 1s state, the ground state, and then there's the 2p state, right? You all remember the 2p state, angular momentum 1, intrinsic angular momentum 1? The 2p state is unstable. It decays through the emission of a single photon back to the 1s state, and therefore it has some lifetime. So as a simple homework problem to show how powerful this is, use exactly the technique I told you here to estimate the lifetime of the 2p states of the hydrogen atom. By the way, experimentally, it's about 10 to the minus 9 seconds, right? It's a nanosecond. And think about it before you do anything, and it should take you all of 5 minutes to do it, whereas, again, it's a whole lecture in the quantum mechanics course. Okay, so that's an aside. Now, so it's very clear how to proceed in general. For any given process that we're interested in, you identify the objects involved, the particles. You introduce fields appropriate for those particles. You construct the interaction of the lowest dimension, and you compute. Very simple. Maybe it's a process for which you demand very high precision. Okay, it's not likely that your precision is going to be parts in 10 to the 12, but if it were for this process, you can handle that too. You just have to include the operators that contribute at that level. Because the addition of derivatives or fields always increases the dimension of the operator and hence decreases the size of its contribution, no matter what precision you want to impose, there's a finite set of operators that are important for it. The technical term is relevant. You need to keep all operators that are relevant given the precision of the observation to compare with. Okay, so if we wanted to go to 10 to the 12th precision, it's one extra operator. So now it's two operators instead of one. You can still go ahead and calculate with those. Everybody clear about that? Okay, now one of the downsides of this whiteboard is that I believe there's only a single page and I have to erase the whole thing. So no record of what we did before, bye-bye everything. Okay, sorry about that. Okay, now the procedure that we just introduced actually grew out of trying to understand the strong interactions in the 1960s. Where, in fact, a straightforward approach of trying to figure out in detail what the interaction is in the same way that electromagnetism had been dealt with 150 years earlier was not practical. But it was gradually understood throughout the 1960s, especially with the work of Steve Weinberg, how this whole effective field theory thing happens. And remarkably, in the 1970s, a very, very smart young physicist named Ken Wilson realized that this whole thing can be turned into a highly technical, rigorous formalism. It came to be known as the renormalization group. And Ken Wilson's work is really the foundation of our understanding of modern quantum field theory and the Standard Model. Of course, I do not have time to discuss it in detail. But one of the simple outcomes of Wilson's idea is pretty easy to describe, so let me do that. So Wilson's starting point is that at any length scale, the proper action includes every conceivable interaction. So the OIs here are the, for example, if we were talking about the light nitrogen molecule scattering, the operator OI includes the O1, if you like, is the operator we wrote down for that interaction. O2 is the one with extra derivatives. But every operator is present in the Lagrangian. But this Lagrangian is the one that's appropriate at a certain length scale. So all those all those coefficients actually depend on the length scale. That is, there's no fundamental Lagrangian works for everything. There is a Lagrangian that works in a certain range of momentum. So when we talked about the nitrogen molecule example, we already argued we do not need to know anything about quarks. We don't need to know about the strong interactions. The Standard Model Lagrangian for those momenta scale really just involves the molecule, not even the atomic physics, and the electromagnetic field. So Wilson's starting point is, forget about this notion that there is a fundamental Lagrangian which describes everything. The Standard Model depends on the length scale at which you are probing nature. Now, maybe someday someone will come up with a unique string theory that describes the universe completely and physics will be over as a profession, it's all done. Most physicists think that's pretty unlikely, even the string theorists. Instead, there's an implicit assumption that as you change momentum scale, what you would call the appropriate Lagrangian of the model for that scale will change. So Wilson incorporated this explicitly. So at some length scale, those coefficients have values, but their values change depending on the length scale. In particular, this is that lambda is corresponding to the Bohr radius, or 1 over the Bohr radius in the analysis we just did. Some operators have lambda 1 over the Bohr radius to some power. The higher the dimension operator, the more powers of the Bohr radius, or 1 over lambda. So Wilson's argument is that when you look at momenta p that are much less than the scale lambda, then if Ci will go like lambda to some power. That power depends on the dimension of the operator OI, as we just saw, and the net effect in any process for some matrix element squared. So some matrix element squared is going to go like p, well, lambda over p, sorry, to the 2 delta I. So when delta I is positive, the effects of this operator grow at long distance. If delta I is negative, the effects shrink at long distance. Does that make sense? So we only have to keep those operators for which the I is positive or 0. Well, it's easy enough to figure out what that dimension should be, because we get a -4 mass dimension from the d4x. So if an operator O has mass dimension 4, then the Ci will be independent of lambda. If it has mass dimension greater than 4, the Ci will have inverse powers of lambda and become small at long distance. And finally, if OI has a dimension less than 4, then the Ci will grow with lambda and become more important at long distance. Okay, and that's the bottom line. Now, I will repeat, there's a lot to this. There are rigorous proofs, and you know, Ken Wilson won the Nobel Prize eventually for this work, not just because he did a little bit of dimensional analysis. But the bottom line is actually pretty simple. Operators of dimension greater than 4 become irrelevant at long distance. If you remember one thing from these lectures, this is the thing you should remember. So most of you have had, I think all of you have had some field theory. When you learn field theory, you were probably taught some concept called renormalizability. And many of you were probably taught that theories which conclude operators of dimension 4 or less are special. They are renormalizable, and those are the important theories. Those are the theories that make sense. In fact, many of you, I hope not too many of you, probably learned exactly that theories with operators of dimension bigger than 4 are non-renormalizable and therefore are excluded from physical consideration. Why do I think some of you might have learned that? Because that's the way field theory was taught for decades. That was the dominant view of quantum field theory and what was the then standard model in the 1950s and the 1960s. Let me say that again. In the 1950s and 1960s, there was an idea that quantum field theory, the combination of quantum mechanics and relativity, was so tricky and so highly constrained that there would be a more or less unique theory that resulted. And the condition of renormalizability was one important constraint that restricted the kinds of theories that could be considered. It was thought of as a strong input on the kinds of Lagrangians that could be descriptions of nature. Is that something familiar to any of you? Our view of this has completely changed. Our view currently, and has been the case for 30 years or longer, is that that viewpoint is just completely wrong. It is absolutely not the case that renormalizable theories are the only ones that make sense. They are therefore special, and we should only look at them. It's exactly backwards. What Wilson has said is renormalizability, a Lagrangian that only has operators of dimension 4 or less, is not an input, it's an output. If we assume the theory includes every possible interaction at short distances, that is high momentum, and we take that theory with all of its complicated higher dimension interactions and ask, what does it look like at long distances? Well, the little argument we've just been through says only the operators of dimension 4 or less make large contributions at long distances. All the other operators are suppressed by powers of p over lambda. This is the point. It's not that renormalizability is a principle that must be applied. It's that as long as we are asking questions at length scales that are long compared to any intrinsic length scale, that physics will be described very accurately with only the dimension 4 or less operators. Okay, I'm going to pause and ask for questions because, again, this is the heart of our modern view of field theory and is the single most important thing I have to say in these 3 lectures. Anybody want to ask a question? Do you dare to ask a question? I take it that's a no? Okay, everybody's still there? Still awake? Somebody say something?
Yes.
I can say something.
I'll follow you.
Okay. Great. So, these are supposed to be lectures on the standard model. So why did I spend 1 out of 3 lectures on this, if you like, baby stuff? Because I can now say clearly what the standard model is. So given what I just said, the standard model is not a fundamental universal Lagrangian which describes every interaction in nature. Okay, you sometimes see that in the popular press in almost exactly those words. No physicist thinks that. That is not what the standard model is. First of all, the standard model is a Lagrangian which applies only in a certain momentum range. If you go ask condensed matter physicists who work at the scale of nanometers and larger, their standard model is not the one that we use as the standard model. Of course, talking about quarks and gluons at length scales that are orders of magnitude larger than the proton or the neutron is a total waste of time. Their standard model has electrons and atoms. Sometimes they don't even need the atoms. So our standard model, the one that I'm supposed to be lecturing about, is a particular Lagrangian that applies in some scale of length or momentum. Anybody care to tell me what those scales are? Nobody wishes to hazard a guess. Well, there's a minimum momentum and there's a maximum momentum. Anyone know what the minimum momentum is? So Julian, the Planck scale, Well, the Planck scale wouldn't be the minimum one because very few of our experiments are taking place at the Planck
It
scale.
would be the maximum one.
Yeah, but okay, but we'll come back to that. So let's start with the minimum one. I just told you that the people who work at the scale of nanometers do not use what we call the standard model. So obviously the length scale is bigger than nanometers. Okay, so I won't torture you. Think about that. You have to understand whether your particular physical situation requires use of what we call the standard model or not. But the more interesting question is that maximum one. So Julian just suggested the Planck scale. Anyone have a different opinion? Everybody thinks it's the Planck scale?
The electroweak
Zibo's on
scale.
that. Well, what is the electroweak scale? So, yeah, electroweak, what, can you give me something in GeV? What's the electroweak scale?
Around 200 GeV.
Great. What are the typical momenta at the LHC?
Tens of
Anybody
TeV.
know? Okay, so yes. So it's actually somewhat less than that because the actual energy, the beam energy, is shared among lots of particles. They come out with less. But so let me see. You just told me that the standard model applies up to 200 GeV. Therefore, it doesn't apply at the LHC?
We hope it doesn't. No? This is the hope.
Sorry, say that again.
This is the hope. We hope it doesn't apply to this scale.
Okay, so Gabriella, of course, has the right answer. The correct answer is nobody knows. We do know the standard model, what we think of as the standard model, is the correct effective description of physics at the scale of 200 GeV. Part of the reason we do experiments like the LHC is to find out whether it is still the correct description at momentum scales of a TeV or higher. Now, in fact, most of us, I'm sure me certainly, Gabriella as well, most of us expected the standard model not to apply at the LHC momentum scales. So far, there isn't much indication that the standard model, that we've reached a scale at which those higher dimension operators are becoming important or new degrees of freedom have appeared. Okay, so that's enough for now. We will come back and talk about this later. We are now almost ready to construct the standard model. Okay, so again, I'm going to pause for 30 seconds. Anybody want to ask anything or complain? Okay, so I just told you how to construct the standard model. You don't need me anymore. So what's the standard model? Yeah, so Julian, the minimum scale. I'll let you keep thinking about that. We'll talk about it. We can talk about it again later. Okay, but basically, well, anyway, we'll talk about it later. So how do we construct the standard model? What did we do in the case of the sky is blue calculation? We identified the appropriate degrees of freedom. In that case, it was photons, and it was a point-like nitrogen molecule. So in talking about the standard model, our first objective is to identify the proper degrees of freedom. Anyone care to give me some clues? I'll get you started. The electron. I'll keep going. The photon. Anybody else?
All the leptons, not only the electron.
Okay, good. Not just the electron, but the muon and the tau and their accompanying neutrinos. All the fermions, that big, great. But which fermions? I mean, we just named 3 of them, plus, well, we named 6 of them because we also named the neutrinos. Anything else? Any particle you've heard of? The quarks, there you go. How many quarks are there? More than that. That's better. 6. Great, 6. Could there be more than 6? Well, not part of the standard model. That doesn't mean there couldn't be another quark. But there can't be another quark at the momentum scales that we are currently probing. Okay. So by the standard model, by definition, it only applies at this momentum scale. It only includes the degrees of freedom we know about. Okay, so quarks, leptons, anything else you would like to include in the standard model? Gluons, excellent. So there's the photon, there's gluons, there's the Higgs boson, there's the W and the Z. Okay, we got them all. Thank you very much. Okay, so all we have to do is introduce the fields for all those particles. And then what do? We write down the most general Lagrangian, including all the operators of dimension 4 or less. And because extra fields, extra derivatives increase the dimension, that's a finite list. So this is now a straightforward exercise. Write down those fields and write down every possible operator. Well, there's a caveat here. I can write down operators that don't conserve electric charge. Should I include those in my Lagrangian? I'm assuming all of you are shaking your heads no, I should not include them because charge seems to be conserved. So there is an issue, is that we don't have to write down every operator. We only have to, we are able to exclude some operators on the basis of symmetries. And indeed, this is our best tool in constraining the form of the Lagrangian in any momentum range. If we know that there are certain conserved quantum numbers, we can build that in. So for the next half hour or so, I want to talk a little bit about symmetries, because this will be an essential ingredient in us reaching finally the actual action of the standard model. So the first important symmetry we have to worry about is one we've already talked about, which is Lorentz invariance. So you probably all know a good deal about Lorentz invariance, but it's a particular symmetry I want to talk about in some detail for the purposes of this school especially, because many of you are working on neutrinos where Lorentz invariance can get a little tricky. So Lorentz invariance restricts the kinds of operators that we can write down, but in addition, it actually also tells us something about how the fields behave under Lorentz transformations, which is essential for understanding which ones are allowed in the Lagrangian and which ones are not. So let's talk very quickly about Lorentz transformations and invariance, and I'm going to leave out all the details because you've all seen this before. So there are 6 generators of Lorentz transformations. Those 6 generators are usually called the 3 rotations. And you know that the generators of rotations are called angular momentum. They satisfy a simple Lie algebra, which is to say rotations do not commute. If you perform one rotation followed by another and then do them in the opposite order, you get a different answer. In addition to the 3 rotations, the additional 3 generators for the Lorentz group generate so-called boost transformations. The boosts can be in any one of 3 directions, therefore they behave under rotations like any vector. So they have a simple algebra. Finally, and kind of interestingly, if you look at the commutator of 2 boosts, you get a minus I epsilon jk jk. The commutator of 2 boosts is a rotation. This algebra is called SO3, 1. This is the group algebra for Lorentz transformations. Why SO3 comma 1? SO3 is the group of rotations. If we had the group of rotations in 4 dimensions, it would be SO4, the set of rotations that leave a 4-component vector's length invariant. But because time comes in with the opposite sign in the length, that's why it's written as SO3 comma 1. Okay. So what do we want to do with this invariance? Well, we want to construct representations of this algebra so that we can deal with our quantum field theory. But it's important when we do this to understand that we want to do 2 quite different things. The first thing we want to know is how the states in the Hilbert space behave under Lorentz transformations. So whenever we have a symmetry and we want to know how the states behave under the symmetry, the states group themselves into what are called representations, that is, sets of states that mix up under the symmetry transformation. So, for example, if we talk about rotations, if we have a vector, a spin 1 particle, that is a particle that carries angular momentum 1, then there are 3 different states that mix up under a rotation. We could also have angular momentum 1/2, in which case there are 2 states that mix up. So with SO3 comma 1, we really want to know how the states mix up under Lorentz transformations. So how things mix up under an algebra are called representations. 2 different representations will not mix up under the transformations. Only the states within a representation mix up. Now, for states, we want so-called unitary representations. Why unitary? Because we don't want a transformation on the states to affect probabilities. If I take 2 states and I compute some matrix element, and now I rotate both states, then I shouldn't get any, if the world is invariant under rotations, I better get the same transition matrix element. So a rotation will happen by the action of some operator, which I've called U, on the state chi, and I want to do the same action on psi, so it's a U dagger on the other side. And I want this to not change the probability, and a very famous analysis by Eugene Wigner concluded that aside from certain very special cases, this requires that the operator that implements the transformation U has to be unitary. U dagger U is equal to 1. So to understand how the states transform, we need to find the unitary representations of the Lorentz group. But as we just discussed, we also want fields to correspond to our observables. So we also need to know how the fields are going to behave. Remember, the fields create and annihilate the particles in the Fock space. But for each kind of particle, there's only going to be one field that creates or annihilates it. So there's no need for unitary representations for the fields. We just want finite dimensional representations. Why finite dimensional? Because if we have an infinite number of fields, we would have an infinite number of particles, which is not what we want. It is absolutely crucial to recognize the distinction here. Otherwise, we end up with all sorts of confusions. So I'm just going to tell you the answer. You can find this discussion in any good book on quantum field theory. Weinberg has an extremely nice discussion in his textbook. The states in a representation are labeled by momentum. not surprisingly. A Lorentz transformation changes the momentum by rotations or by boosts. But there are actually two different cases. As you know, a Lorentz transformation cannot change the length of a 4-vector. So the momentum is a 4-vector, and its length will not be affected by a Lorentz transformation. So a given representation is labeled by that length, otherwise known as the mass squared. When the mass squared is positive, the representation is also labeled by spin, which is a half integer. So that's the easy case. What's a little trickier is when m squared is equal to 0. In this case, Lorentz transformations act a little bit differently. And the representation is not labeled by spin, it's labeled by helicity. Helicity is the component of spin in the direction of motion. So in particular, for a representation of a massless particle, Lorentz transformations cannot change the helicity. Whereas if I have a massive particle in spin, I can change the spin by doing a rotation, for example. Okay. Therefore, when I'm constructing the Fock space for massive particles, I have to also ask what the spin of those massive particles are. For example, we know that the pion has spin 0. We know the proton has spin 1/2. The electron has spin 1/2. Those are all massive things. What about the photon? Well, the photon is massless. So the photon, we do not talk about the photon spin. We talk about the photon helicity. Anybody know what the photon helicity is? One. Very good. So actually, photons come in two different helicities. You learned them early on in your life as a physicist as two different polarizations of electromagnetic waves. For example, left circularly polarized or right circularly polarized. Those are, in fact, helicity +1 and helicity -1. But notice for the photon, there's no helicity 0. There are only two helicity states of the photon. Sometimes people, loosely speaking, say, oh, the photon has spin 1 because it can contribute to angular momentum 1. But that's false. Spin 1 would have 3 states. The z component of spin can be +1, 0, or -1. That's not the case for the photon. Okay. So again, stuff you know. But what about the fields? Well, the fields have to be finite dimensional representations. And again, I am not going to teach you the full representations, but there's actually a little trick that helps us figure out the representations. I can take the 6 generators, and I can rearrange them in linear combinations. Complex linear combinations, but linear combinations nevertheless. I can define a J plus and a J minus, which are simply the angular momentum generator J plus or minus I times the boost generator over 2. Why do I do that? Because when I look at the commutation relations, the J plus generators commute with the J minus ones. And the J plus generators themselves obey the rotation algebra, SO3, as do the J minus. So the algebra looks just like SO3 times another SO3. And you all know the representations of SO3, really SU2. They are labeled by a half integer, and they are what we usually call spin, or angular momentum. So the field representations of the Lorentz group are characterized by two half integers. The number of fields is 2s plus 1 times 2s minus plus 1. That's because the spin s plus representation goes from s plus minus 1, s plus minus 2, all the way down to minus s plus for the z component. So that's 2s plus 1 pieces. And then there's 2s minus plus 1 for the s minus. Okay. So you are familiar with most of these representations. Let's start writing them down. Well, the simplest one is 0, 0. That's a single field, otherwise known as a scalar field. Of course, if we use such a field to create and annihilate particles, it's going to produce a Fock space just like the one we talked about before. No spin, no internal angular momentum. The next representation we could look at is 1/2, 0. This representation is two-dimensional, right? Jz on the left side is plus a half or minus a half. So this will describe, in principle, a massive particle, if we so choose, depending on the Lagrangian, which will then have spin 1/2, or equivalently, a massless particle of helicity 1/2. This is called a Weyl spinner. Of course, there's another one, which is 0, 1/2, which is also a 2D representation, which is also a Weyl spinner. There are two different Weyl spinners. One of them is called a left Weyl spinner, and the other is the right Weyl spinner. Actually, as you can see from that I, if I consider the representation s plus s minus, and I take its complex conjugate, it's going to turn what I call j minus into j plus, and vice versa, just because of the plus or minus ik. So if we consider the left Weyl spinner representation, and I introduce some field corresponding to that representation, so a two-component, two fields for that, and I take its complex conjugate, it'll be a right Weyl spinner. So what is the 1/2, 1/2 representation? First of all, how many components is it? Well, it's 2 times a half plus 1 times 2 times a half plus 1, that is to say 4. This is the 4-vector representation. Okay, one last one. One comma 0, and then I've added together with it 0, 1. This is the representation appropriate for the electromagnetic stress tensor. It has 6 components. Okay. Now, part of the reason why I have gone through this is because I know many of you are working on neutrinos, and I want to ask you to do me a favor. So you've all heard of Weyl spinners. Well, now I've said what the Weyl spinners are, but you've also heard of a Dirac spinner. How many components are in a Dirac spinner? Well, we use a Dirac spinner to describe the electron, and there are 4 components in it. In fact, we can think of those 4 components as something which annihilates the spin plus a half particle, something that annihilates the spin minus a half particle, something that annihilates the spin plus a half antiparticle, and something that annihilates the spin minus a half antiparticle. 4 components, 4 fields needed. So here's the trick question. What representation of the Lorentz group is this? Can someone answer? Anybody know? Yeah, Omar, thank you. Which product is it? So it has 4 fields in it. Yeah, good. So Omar suggests it's 1/2, 0 times 0, 1/2. But I can multiply. Remember, this representation is one-dimensional. It has a single thing in it. So when I multiply it by this one, which has 2, I still end up with 2. And when I multiply this one with this one, I get another one. So that product is the 1/2, 1/2 representation, which is a 4 vector, which is not a Dirac spinner. Anyone else want to try? Nicolo, thank you. So, and Ting, so many of you. So you all know the answer. It's actually a sum, not a product. It is a 1/2, 0, we call it a left vial spinner plus a right vial spinner. So what does it mean to be plus? It means there are just 2 different things here, and they do not mix up under Lorentz transformations. So here's my favor, which I would like to ask of all of you. Stop using Dirac spinners. Never use them. Just use vial spinners. So before all of this was well established in the community, there was skepticism back in the 1930s that vial spinners would ever be relevant in nature, that everything would be Dirac spinners, because the only spinner that was known at the time was the electron and Dirac spinner. And it took a very long time before it was appreciated that there actually are vial spinner fields that are useful in the standard model. And so people routinely write those as Dirac spinners and then project them down onto the different components, which is extremely annoying. And so most physicists who work on subjects outside of neutrino physics just use vial spinners religiously. So I strongly encourage you to learn how to work effectively with vial spinners and stop using Dirac spinners, especially in trying to understand the standard model. So why? Well, since Lorentz transformations don't connect the 1/2, 0, or the left vial spinner with the 0, 1/2, the right vial spinner, you could always have just decomposed it and written as separate things, and they would never talk to each other. Now, there might be other symmetries or interactions which would connect them, but there aren't necessarily. And in fact, because Lorentz transformations do not connect the left part of a Dirac spinner with the right part, it means the physics of the left part does not have to be the same as the physics of the right part. And indeed, that's the case in the standard model. Theories in which you don't have identical physics between a left spinner and a right spinner are called chiral. The standard model is an example of a chiral theory. Chiral theories are much easier to talk about and to calculate in if you use vial spinners. So I am going to only use vial spinners in my discussion of the standard model. The next comment I wanted to make, though, is that of course, a Weil spinner like 1/2 0 is necessarily complex, because remember we had that j plus or minus ik. And so if I have a left Weil spinner, its complex conjugate is a right Weil spinner. So if I introduce a field to include corresponding to some particles and include in my standard model, of course I will want the Lagrangian to be Hermitian. And so if there's a psi L that appears in various places, there will also be a psi L star that appears. And that means that I will have both psi L and psi L star. So in choosing which one I want to call the thing without the star and the one with the star is entirely conventional. So the convention that most of us use is all fermions without the star are 1/2 0. Okay, you could equally well have chosen 0, 1/2, but this is the way we will be operating. Okay. I'm way behind, got to get moving. Okay, any questions here? I got 25 minutes left and I got 50 minutes of material. Questions? No? Okay. So for the remainder of today, we want to talk about other symmetries that will constrain the operators in the standard model. We talked about Lorentz invariance. That's straightforward. You've all seen a discussion of that. In addition, there are things called global symmetries. Generally, global symmetries are transformations of the field which leave all observables at the space-time location x still at the space-time location x, but may mix up the fields in some other way. So I've parameterized them with some lambda. For example, a space-time rotation is not an example of this because it mixes up the space-time label. A phase rotation for a complex field is a good example. As you all know, by Noether's theorem, there is a connection between transformations that leave the action invariant and conservation laws. For every global transform that leaves the action invariant, there is a current that is conserved. Okay. So you've all seen this. I'm going to leave out the actual derivation of Noether's theorem. If you've never seen it before, ask me and I'll show you. Yeah, Satvi, good. So, yeah, I got it. So we will see some transformations. So I wrote down the transformation phi of x goes to phi of x and depends on some parameter, and I gave an example. Phi of x goes to e to the I lambda phi of x. Or maybe I've got two fields, phi 1 of x and phi 2 of x, and I transform them into phi 1 of x cosine lambda plus sine of x, sorry, sine of lambda phi 2 of x and the orthogonal one. In all these cases, these are transformations in which I start with some observables at the space-time point x, and after the transformation, I still have observables, different observables, but at the same space-time point x. That's called a global transformation. Global because it was point-wise on space-time. I never mixed up observables at different points in space-time. This is called a transformation, a global transformation. It's called a global symmetry if the action is invariant under this transformation. Okay, did that answer your question? We can also consider transformations which take observables at one space-time point to another space-time point, like Lorentz transformations. Okay. Okay, I'm trying to reduce things on the fly. Oops. So for that conserved current, it turns out that there are some important consequences in QFT. The first, one of the important consequences is to consider what happens if we insert a current in some matrix element of a bunch of operators. Well, the current is supposed to be conserved, so I can take the forward divergence of this thing. If it weren't for the fact that the matrix elements we compute in quantum field theory involve this time ordering, and I'm assuming you've all seen that in field theory, this would be simple. The divergence of J is 0, and this would just be 0. But the time ordering says that there's some hidden time dependence in here, and so when we take this derivative, it can act on the time component, and because of that, we get a sum of terms in which we get commutators of the time component of the current with the fields. Now, the time component of the current is related to the charge. It is the charge density. So that time component of the current integrated over space is the generator of the symmetry, and so this transforms the field phi. If the field phi carries one of those global charges, this is the charge times phi, so it's a measurement of the charge. Now, why is this interesting or relevant? What it tells us is that if I look at one of these Green's functions, and I take the divergence, I get a minus I, which is unimportant. I get a sum of all the charges. The details of this are not very important, as we'll see in a minute. So this relation is called the Ward identity. If we Fourier transform, this becomes a K mu, and this becomes an EI K dot xj. So why did I waste the time to write this thing down without explaining it very much? So here we have the vacuum expectation value of a bunch of operators phi, which carry charge Q. On the left-hand side, we have some matrix element, I don't know much about it, and then I have a K mu dotted into it. What happens as K mu goes to 0? Well, since there's this explicit K mu on the left, when K mu goes to 0, this thing must go to 0. So we expect this to be 0. This complicated little argument is just a very fancy way of saying the expectation, that the vacuum expectation value of anything that carries net conserved charge must be 0. The vacuum doesn't violate charge conservation. This is called Wigner-Weil. And it was not realized until the early 1960s that there's an alternative. Is it possible for this to be non-zero? Well, yes, if this has a pole. And what at the time was a pretty shocking discovery is that this Ward identity, which until the early 60s had been thought as ensuring that the vacuum did not violate any charge conservation, actually said no such thing. It said that it's possible to have no charge violation, but if you have charge violation, if the vacuum expectation value of some operator that carries charge is non-zero, then Green's functions must have a pole at k squared equals 0. That is to say, there must be a massless particle. Anybody know what that massless particle is called? Yeah. It's called a Nambu-Goldstone boson. It corresponds to, so if the vacuum succeeds in not reflecting charge conservation by allowing some operators that carry the charge to have a vacuum expectation value, then inevitably there is a massless particle called a Nambu-Goldstone boson. Does the standard model have any of these? Photon. So one thing that I did not say, but also follows from the same analysis, is that a Goldstone boson has to be a scalar representation of the Lorentz group. So it can't be the photon. But, right, not a scalar. So not the photon. But a good guess. You did the right thing. You said, are there any massless particles? It's got to be a massless particle. So there are no Goldstone bosons in the standard model. So through the Higgs mechanism. So since there are no Goldstone bosons in the standard model, why did I bother talking about them? Well, because I want to talk about the Higgs for a minute. So for the Higgs field, for at least this simple demonstration, sorry, I didn't want to do that. I'm going to consider a complex scalar field with two components and a global symmetry SU2 cross U1. So SU2 is the same as SO3, so this is the spin 1/2 representation. And I'm going to call it isospin so you don't confuse it with the Lorentz group. And I'm going to refer to the U1, which is just a single generator, some kind of charge. I'm going to call it hypercharge. So my complex scalar field is going to have two components. And for very odd reasons, the upper component I'm going to call phi plus, and the lower component I'm going to call phi naught. But at the moment, those are just names. I could have called them A and B. So remember what it means to say there's a global symmetry. It means there's a transformation of the field H under which the action is invariant. So the U1 transformation is simple. H of x, the two-component thing, goes to e to the I lambda h of x. And more interestingly is the SU2, where it looks like a two-component vector. In complex notation, we use the Pauli matrices. Acting on H. I now have to construct a Lagrangian that is invariant under this, but that's pretty easy because both of these factors are unitary matrices, which means if I multiply one of those factors by its Hermitian adjoint, it becomes the identity. So for Lagrangian, I will take, well, the usual kinetic term, and then a potential. And for the potential, I'm going to include, well, let me write this, and then I'll explain what I've included. Something which goes up to quartic order in H. So how did I arrive at this? Well, first of all, I wanted to ensure that it's always H dagger H so that it was invariant under those unitary transformations. But why didn't I include H dagger H to the 12th power? You remember our conversation earlier about only needing to keep operators of dimension 4 or less. You can easily verify that the dimension of H is 1, and consequently, I don't need to include anything more than a quartic potential. So this is actually the most general Lagrangian for this field carrying this global symmetry of dimension 4 or less. Although I've written this as v squared, in principle v squared could be a negative number, up to you. In quantizing this theory and trying to identify the vacuum state, we should figure out what the minimum of the potential is and then do the quantum mechanics of the oscillations around that minimum. Clearly, if v squared is positive, the minimum will occur when h dagger h is equal to v squared over 2. Of course, h dagger h equals v squared over 2 implies immediately that the individual components of h cannot all be 0. If they were, h dagger h would be 0. And consequently, when we quantize this system, we've discovered that the vacuum expectation value of h will not be 0. Well, we're now in exactly the situation that we talked about before. Rather than the Wigner-Weil realization of the symmetry, we are in the Nambu-Goldstone realization of the symmetry. A field that transforms non-trivially under the symmetry transformation has a non-zero expectation value. So our previous argument says immediately there is a Goldstone boson. Sorry. Okay, let's see if we can find it. So in figuring out what the vacuum expectation value of h is, we actually have a lot of freedom, because we can use the symmetry, that SU2 cross U1, to transform this any way we like. So first, we can use the SU2 symmetry to ensure that only the lower component is non-zero. Then we can use the U1 transformation to ensure that V is real and positive. Okay, and then its magnitude must be V over root 2 to satisfy the minimization of the potential. But notice, so the language we use is that this vacuum expectation value breaks some of the symmetries, and associated with each breaking is a Goldstone boson. Notice in this case, we have 4 separate currents. 3 currents associated with the SU2, which has 3 generators, and a 4th one with the U1. So we have to ask, did we break all 4 of those generators? If we did, we would have 4 Goldstone bosons. If we only broke 1, we would have 1 Goldstone boson. In fact, we can easily see that if we take the 3rd generator of isospin, T3, which acts as 1, 0, 0, minus 1, and the hypercharged generator just acted as the identity, if I add them, then this transformation this should have been 1/2, excuse me. And that's a 0. This transformation does not affect the vacuum expectation value. So we didn't quite break all the symmetries. That is, there is a residual symmetry. We started with a global symmetry of SU2 cross U1, but the vacuum was only invariant under a U1. That U1 was a combination. It mixed the generators of the SU2 and the U1. Okay. So, in fact, we then expect that we broke 3 generators out of a possible 4, so there should be 3 Goldstone bosons. And we just have to find the currents associated with them. Not too surprisingly, it is, in fact, the generators of SU2, if you like, the T1 and T2, plus the orthogonal linear combination of, say, T3 minus Y. It is quite convenient to parameterize the general Higgs field as the vacuum expectation value times some unitary transformation and the 3 pi's are the Goldstone bosons. By plugging this back in, you can easily see that the effective Lagrangian of the pi's does not have a mass for the pi's and that they are the Goldstone bosons. Okay. So, sorry for the rather boring recap of what is known as spontaneous symmetry breakdown. But I wanted to talk about it in this language because at the moment, this is exactly how we would describe the Higgs field. And indeed, this little theory that we wrote down is precisely the one that was introduced by Higgs and then Weinberg in his model of leptons. But as we said before, there are no Goldstone bosons in the standard model. Yet this little description of the Higgs has led us to 3 Goldstone bosons. So what happened to them? Well, as you all know, there is something known as the Higgs mechanism, which changes this picture. So we are at the end of this lecture. As I said, I'm a little bit behind. So at the very beginning of tomorrow, we will flesh out the Higgs mechanism in a very simple way. And then we will finally be able to actually write down the standard model and get to what I'm really aiming at, which is what's wrong with the standard model. We'll spend the bulk of tomorrow doing that. So I apologize for the dryness of this recap of spontaneous symmetry breaking and my slowness and getting behind, but we'll pick things up tomorrow. Okay, so thanks.
Thank you. Are there any questions? If there are no questions, can we go back to the lowest scale, or are you going back to this tomorrow?
Sorry, was that a question for me? I didn't quite hear.
No, I just asked whether we can go back to the lowest scale where the standard model is valid. Okay,
Yeah.
no, the students have priority.
Oh, we have some questions.
Yes, we have some questions from the students.
Okay, so let's start with Zihong. Why is the ordinary derivative not a covariant derivative? So excellent question, because I am so far, whoops, wrong thing. Because at the moment, I haven't said anything about the W and Z bosons, or what we know are called the gauge interactions. I have not put them in yet, which is precisely why we seem to have found an incorrect answer of 3 Goldstone bosons. So our goal for tomorrow, the first thing we will do is put the gauge interactions in and try to understand what happened to them. Okay, did that answer your question? Exactly. So Argyachit is exactly right. So we were treating this as a global symmetry. We will try to understand what happens when we try to include the gauge interactions tomorrow. Okay, other questions? I know this was dry and you're tired, but if there's anything else, go ahead.
Okay, if there are no further questions, we have a lunch break now. We start today at 3 and we meet Andy tomorrow at 10 for the last lecture. Thank you very much for these fantastic lectures.
Okay, Thank you. For me, it's good night. I'll see you all tomorrow.